My name is Ariel Lellouch, and my work seeks to understand if we can find better ways to study faulting and structures in the subsurface with fiber optic sensing.
Hello, my name is Andrew Geary, and welcome to Seismic Sound Off in-depth conversations in applied geophysics. In this episode, Ariel Lellouch discusses his upcoming Middle East and Africa Honorary lecture, Applications of Fiber-Optic Sensing to Borehole Seismology. Distributed Acoustic Sensing, or DAS, is an emerging technology that leverages optical fibers to record the seismic wavefield with an unprecedented spatial resolution. In this conversation, Ariel makes a case for geophysicists to utilize DAS data in their work and why it's essential to look at data without any pre-made ideas. He also outlines the significant benefits of vertical DAS arrays and how to know when to use vertical or horizontal DAS. This is an excellent primer on distributed acoustic sensing and a convincing case for why every geophysicist would benefit from engaging with this technology. This episode is sponsored by Geospace Technologies. For decades, Geospace has delivered robust data acquisition systems of all scales. Geospace's PRM solutions were the first to provide a 4D understanding of marine reservoirs. Today, Geospace leads with opto-sized fiber-optic sensing technology for reservoir monitoring. Recently, the company launched a reduced sensor footprint solution using compact phased array technology for passive monitoring of microseismicity known as SADAR. Learn about the latest advances in reservoir intelligence at geospace.com. And now my conversation with Ariel Lellouch. Your honorary lecture that is upcoming is called Applications of Fiber Optic Sensing to Borehole Seismology. So what is the goal of this lecture?
Right. So, honestly, I would say trying to convince other geophysicists to use DAS data in the seismic band. As you know, these days, the downhole fiber data acquisitions are becoming more and more common. And there's a ton of data that's been recorded, but not always fully utilized. So in this talk, I'll show several examples of what you could do with DAS data, but these are some ideas. That there's a lot of room for new ones. So I would say maybe try to get people excited about it and try to get people to look at their own data and maybe, look for new interesting things to find.
I like the idea of trying to persuade geophysicists in a new route. And what is just a brief primer on distributed acoustic sensing, or DAS?
Right. Yeah. Maybe we should have started with that. But I know it's becoming more and more popular these days. So maybe most people have heard at least something about it. So we all know about optical fibers because we see them or use them in our daily lives. And in this context, they act primarily as, let's say, so-called ideal transmitters of light. Light can also be information, of course, so we can use them for internet. Now, with DAS, we actually use the very, very tiny portion of light that doesn't go through the fiber and is instead reflected back to its source. And we use a special, very complicated system called an optical interrogator. And this system sends pulses of light into a fiber and analyzes the light that is reflected back to it. So if you want the non-ideal part of light going through the fiber. And it turns out that if you analyze the changes in the patterns of the reflected light, you can actually tell how much the fiber is elongating or compressing at each position along the fiber. And you can do this with a very, very high resolution in both space and time. So in fact, you're turning an optical fiber into a very dense seismic sensor that measures elongation or compression, technically known as strain. Basically, the important thing is that an optical fiber becomes a seismic sensor, which is very dense.
Yeah, with just so much information that geophysicists need to know, it's so hard to know, what common ground you're standing on with especially with newer technology. Why does improving spatial resolution matter?
Right. Yeah, and I think that's really the main benefit of DAS. So first of all, and every geophysicist would relate to this. You want to generally avoid aliasing. So if you're interested in very short seismic wavelengths, or you want to study very fine structures, coarse resolution means you could simply miss your recording target, right? Because you cannot record something that is significantly shorter than the spacing between your receivers without aliasing. So just for example, in my talk, I'm going to mention some very cool guided waves we could study using DAS. And I realized this was a pretty extreme case for seismic, but we saw wavelengths that were only a few meters long. And that means you need the spacing between receivers of, 1 to 3 meters, something like that, to be able to record it properly. And this is very difficult to do with conventional geophones. So you can say that without the DAS spatial resolution, we just missed this part of the wavefield. We just could not study these waves at these frequencies. So that's one aspect that's, in a sense, more obvious. The other one, I think, has to do with data processing. These spatially separated measurements are, to a large extent, independent, maybe except points that are very close to one another. And that means that you're going to see the same event or the same seismic phase over many different recording locations. And that means you can detect events that are kind of drowning in noise because they're going to be present in over hundreds or thousands of measurement points. You can overcome the noise and you can better understand how these signals propagate in the subsurface because you have this very high resolution and you can track the arrivals of the seismic waves very precisely. So that's another aspect of the spatial resolution. It's going to really help in data processing and overcoming noise and complicated structures.
So they're kind of, a general two types of DAS with vertical or horizontal. Is it fairly straightforward where one would use one or the other?
Yeah, that's a very good question. I mean, both offer this great resolution. My notion, and maybe it's not the most scientific answer, but I think that many times it's dictated by existing infrastructure. So, for example, you can look at horizontal DAS at near surface level. You can do it by piggybacking on existing telecom fibers, for example, which significantly cuts down on time and effort. Now, if you're talking about downhole, as in this lecture that I'm going to give in a few months, then again, I think it really depends on the well. If you're looking into an unconventional reservoir, deviated and eventually horizontal wells are going to be quite common. So that's the DAS recording you will have. And, because downhole operations are usually expensive and complex and involve many people interested in, I think the well design often goes first and the DAS recording kind of follows. So, we as geophysicists, I think, need to be able to do something with any type of DAS recording, whether we think it's ideal or not. That's, I would say, the more practical answer. On a more ideal notion, I would say, I think that one of the limitations of DAS is the directional measurement. So DAS measures something along the direction of the fiber, and this can sometimes complicate data processing and algorithms. So for me, of course, the best acquisition would be a combination of both horizontal and vertical, so you can get different directions of the seismic wave field, hopefully different seismic phases, and ideally do so in multiple wells. But of course, that's just the idealization. And as I said, in reality, sometimes you're just piggybacking on what you can get. And I know it may sound negative, but I think it's actually one of the great strengths of DAS is that for some cost, which is not tremendous, you can get a lot of data. And it's not like with conventional geophones where you need to drill a dedicated monitoring well that's going to be very expensive, et cetera, et cetera. With DAS, you just take the well, make some additional effort in installing the fiber behind the casing, something like that, and then you can record even in a flowing well without too many issues. So it's kind of a blessing and a curse, this kind of piggybacking strategy.
Yeah, it's nice to know, maybe there's situations where you don't even have to decide a vertical or horizontal. I was kind of amazed reading your talk about how much a vertical DAS array can do. It could construct velocity models, locate and estimate the magnitude of earthquakes. What makes these vertical DAS arrays able to process so many things at once?
Right. So, I mean, we talked about the spatial resolution earlier, and I think just the number of measurement locations we get is eventually the key. I mean, if we had hundreds of thousands of dense downhole geophones, we could do amazing things and maybe even more amazing things. It's just, for me, DAS, at each measurement point, let's call it a virtual point, is an okay plus sensor. It's not incredible, but just having so many of them for reasonable cost just tips the scale. And I think we can do so much with vertical DAS just because we have so many measurement points. So yeah, it's a numbers game eventually, at least the way I see it.
Yeah, I'm not sure if this next question is kind of related to everything being discussed here, but looking at guided waves, which are particularly short, you say less than 10 meters in wavelength, is that why DAS is well suited to record guided waves, just the sheer number of arrays you're able to set up?
Yeah, exactly. And I mean, I hinted to this already, but I mentioned that we need to avoid aliasing. So if we have these very short guided wavelengths, we need a very dense array to be able to record them without aliasing. But the other aspect is what you mentioned is thanks to DAS, we can actually have receivers inside the reservoir, which is the waveguide. So we are actually able to follow the propagation for a very long distance. So we have very dense measurement, but also very long measurements. And therefore, by doing so, we can analyze the propagation properties of these guided waves and very surely say that these propagation properties differ from regular seismic body waves. And again, wells that reach the reservoir, and I'm talking about unconventional, they're eventually designed to be flowing fluid. So deploying geophones or other sensors in them is very inconvenient, right? You would usually need some dedicated monitoring well, which is expensive and so on. So DAS lets us record not only with this like unprecedented resolution, but also in the world in locations that would be very impractical to work with conventional geophones. So again, it's a combination of density and extent and where all this recording happens.
Why are guided waves susceptible to open fractures that are induced by hydraulic stimulation?
Right. Yeah. So this is a very, very complicated question. I would say, generally speaking, the interaction of seismic waves with open fractures is quite complicated. You've got a lot of effects in play. And, I don't want to get into too many details. I mean, I would say my primary intuition is that the fact that the guided waves, as the name hints, never leave the reservoir, right? They're basically confined to the reservoir. They have no way of evading these fractures. I mean, they have to tackle them head on. And body waves may sometimes, circumvent these fractures because they can follow the velocity structure. And guided waves cannot do that. So you basically have these guided waves, they have to go through these fractures and they have to go through all of them. And because the fractures, again, at least hopefully, are mostly within the reservoir, this is the densest area of fractures and we have to go through it. So that's why I think intuitively these guided waves tend to be more effective. And another aspect that we see is that this is mostly true for shear wave guided waves. We also see an effect on the pressure wave type guided waves, but the effect is less noticeable. And I think this, again, makes sense from like very basic rock mechanics. If you have an open fracture, the shear wave velocity, at least locally, drops to zero, right? You've got air, for example, so you have no shear. And I think that's why for these guided waves, they encounter a very sharp transition from basically formation velocity down to zero. So it makes sense that they are affected. Now, of course, it's really super complicated physics. And what I'm going to be talking about is still very preliminary analysis and kind of first order stuff. And again, there's a lot of modeling studies and theory to be completed. But at least in first order, it does seem that the shear wave guided energy is much more influenced, which makes sense, again, from rock mechanics.
Yeah, this is going to be a cutting edge talk, which is kind of exciting. How is it possible to locate microseismic events despite the unidirectional nature of the DAS measurements?
Yeah. So we hint is going to be with guided waves. So usually when you have a single DAS line, or you kind of linear element, whatever, it can be horizontal or vertical, it's generally insufficient for location because you have this circular symmetry around them, right? Because DAS only measures one component of the seismic wavefield. So if you've got a line, you've got this circle around it, you can find the location along the line, but not so much the absolute location in space. So the best case scenario to solve this is, of course, having multiple DAS wells. But as I mentioned earlier, this is somewhat of a luxury. However, even for a single well, you can have a special case in which you see this unique behavior of guided waves that I mentioned. And it manifests as dispersion, so different frequencies traveling with different velocities. And it turns out from some studies that we conducted that if you see these guided waves, it means that the source was in or very close to the reservoir. So you kind of got an indicator of knowing, okay, the event cannot be coming from anywhere in space. It has to originate in the reservoir. And if you know that, because reservoirs are usually, unconventional ones, are usually not very wide, they're usually, let's say, bounded by a few tens of meters, at least in the formations that we looked at, you can actually constrain the depth of the source, and then you can, at least to some extent, resolve event location much better, despite having a single fiber. Now, it's important to say you're still kind of stuck with this left-right symmetry for a horizontal well. There is no way of resolving that, at least that I know of. But because of the way the stimulation happens, you can just attribute all events to one side of the well, and then when the other side is stimulated, attribute all events to the other side. So it's not perfect, but at least you can do something with a single recording well in terms of location. And that's a pretty common case. Having multiple DAS wells is something that's picking up, but it's taking time and it's very expensive. So you still can do something with a single well, even if it's only saying which events are in the reservoir and which aren't, which of course from production standpoint has quite a bit of value.
Who is the perfect audience for this talk?
I think that any geophysicist who has worked with seismic data before could find it interesting. I mean, yes, the data will show are from DAS recording, but the processing and the algorithmic mindset will probably be very familiar to those geophysicists. I'd say, as I mentioned earlier, a perfect attendee would be someone who, after the lecture, goes back to their own data and starts digging for interesting stuff, or convinces management to install more DAS fiber and get more data. But honestly, I think really it's just this array processing mindset that's kind of second nature to most of us geophysicists is what you need for this talk. And I think you can enjoy and maybe hear about some cool applications and then think of your own, just because the DAS itself is not significantly different from conventional tools. It's just there's more sensors, more measurement locations, et cetera, et cetera.
It's one of the nice things about the virtual lectures right now is that if you think you have an interest in this, just sign up and listen, and who knows what you're going to find. What is a question you hope attendees will ask themselves after your presentation?
I'd say, again, maybe practical, but can any of my problems be better solved with DAS?
Simple. I like that. What principle, teaching, or point of view has helped you succeed in your field?
Well, I mean, I'm not sure I'm so successful, but I would say maybe, again, despite being in academia, it's going to be a non-academic one. I'd say something like, data haven't studied your theories. In other words, in machine learning, people talk about data-driven approaches, and I think we as humans can and probably should do that as well. I mean, it's important to eventually understand what we observe and have some solid theory to back it up, but we first need to observe and see what in our data doesn't make sense. Like, what are the parts that we don't understand or that we're not using for our benefits? And, just looking at random DAS data, I started and I had completely other things in mind. And then you start seeing guided waves, and then you see tube waves, and you see all sorts of things that you didn't really think a priori you're going to be able to see or even analyze, but sometimes these convey the most information to you. So I just say, look at your data first without too many pre-made ideas, and especially focus on what you don't understand in the data.
Well, last time we had you on this podcast, you won Best Paper for the paper you were discussing. So I hope something equivalent comes to you from this talk. I appreciate you joining us again. And this is a very hot topic. So I'm sure people will be excited to sit in on this lecture and hopefully take some new things that they can then relook at their data and see what else they can do.
Yeah, hope so too.
SEG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary at 51 Features. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.